First thing class. So we talked so far, and we're still not in class time, but just background. We've talked so far about pressures at a point. We realized that pressures at a point rely on the weight of the atmosphere above us and the weight of water above us as we go down in depth within the ocean or in fluids. And we know how to calculate that from things we've talked about. We could also imagine that pressures that act on structures are important. And so we'll talk about that starting today. We know how to get a profile of pressures as they change with elevation. And so we need a formal way of being able to evaluate that. And some examples of problems that have developed with that. One of these is the Malpasset Dam, which is in south of France, in Provence, near Nice. It was built in the 1950s. A thin arch dam, so a very thin shell that goes across the valley, and that is anchored in the walls of a canyon, and so the water behind me pushes against the back of the dam, and the reaction is from the walls of the canyon. And of course, in many of the things that you work on, environmental systems engineers, petroleum engineers, mining engineers, you work less with concrete and things that you fabricate, and more with the geological subsurface, things that you don't fabricate, but you have to characterize and figure out whether they're strong or not. And so this dam, in heavy rainfall, perhaps it's already broken by the time I've been sitting here chatting, in a heavy rainfall, got loaded up. This would be a spillway, emergency spillway over the top, so it can discharge when it gets to the height of the dam, because the dam is designed for a certain pressure. But unfortunately what happened in this dam is that the abutments had some faults in them. The faults shifted and the dam moved. The dam didn't break or rupture. It's still in place. I think I've been within 30 kilometers of that, but never went to see it, but I think it's still in place. And as a result of that, it discharged all the water. Well, I guess it didn't survive, thinking of the Vaillant Dam. And so it discharged all the water and it went down the relatively narrow canyon, because typically you build these dams in narrow canyons to reduce the span that you have to complete across the valley. And as a result, I think it killed 495 people. And so the question is, how do we calculate exactly the magnitudes of the forces that will be acting on the system to be able to see whether there's enough resistance to it? Clearly, there was enough resistance in the dam, but by the abutment shifting, it fractured and you saw the resulting gap in it. So that's an interesting statics, fluid mechanics question we have for today. The dynamics of it is what happens with the pulse of water that races down the valley that killed the 495 people. And so when we talk about Bernoulli, and we'll talk about conservation of momentum, those are the essence of the mathematics, the physics that goes into the models that allows you to do these calculations. I think a pretty elementary calculation in this case. Topography, that you have fluid running across and being able to calculate exactly when it would arrive at some location. And of course, the most recent example of that would be the Texas tragedy of the kids staying in their camps. Big rainfall, can calculate exactly what a big rainfall does to the hydrology, surface water hydrology. You get a massive rain landing here, you know the topography, you can do exactly the same kind of calculation as was done for this, and that was done apparently, but apparently wasn't communicated in an appropriate way to them. Vaillant Dam is another dam, another interesting case, not a dam collapse, but a case where the whole side of a mountain above the reservoir dropped into the dam, dropped into the reservoir, and as a result evacuated all the water over the crest of the dam. Dam still stands today. It's got a lot of rock inside the reservoir that was there, but also killed a couple of thousand people, I think, in the narrow confines. So we're doing death and destruction, I guess, today. And I'll go through this quickly as well. It does work.
On Rome's Ciampino Airfield, 970 miles from London.
Jolly good show!
So, yeah, perhaps you don't need this. So this is the 1950s. This is the Comet. I think it was the very first commercial jetliner. Probably the UK and the US were technologically similar coming out of the Second World War and into the Cold War. Beautiful plane, 2 engines inside the wings, probably terrible to maintain just in terms of cost. And when you fly in a plane, the planes that you choose to fly in, you'd like them to have roughly the same number of takeoffs and landings. And the Comet did not. It would go away and it would not turn up as its destination. It would just disappear. And you can see the shape of the windows there. It's like sitting in a train. It was a mystery as to why this would go away and not arrive at these locations. And the reason was that if you look at square windows, you never see square windows in planes, right, these days. You have a stress concentration at the corner of the windows. And cracks will tend to emanate from there. And that's what exactly happened here. So it would go off merrily to some location. Yeah.
What is its top speed?
No idea. I'd imagine it would be 500 miles an hour. Most jets are, right? It would be the same as those days. Certainly not supersonic, right? First supersonic planes were the Concorde. And the US had one, the SST, Supersonic Transporter, which they abandoned in the 1970s. Concorde turned out to be a bit of a white elephant just because it's too expensive to run. But I think people are looking at supersonic transport again. And so it would not arrive at places. And so what they did was try to figure out what's going on. Of course, you gather the stuff, the wreckage from where you find it. And I'm going through here. And this is, the sad recovery. I think this is off Naples or somewhere, pulling it out. But how can you test for that? Well, what you can do is you can take the plane, you can put buffers around it in a tank. You can put water in that tank, and you can pressurize the inside of the plane to be able to look at the relative difference between the internal pressure and the outside pressure as perhaps a mechanism by which it's falling apart. And so ultimately, you see again the square windows. You take it through a bunch of cycles, so it takes off and it lands, takes off and it lands. So if it goes up to 30,000 feet, we saw that 30,000 feet Everest was something like 20 kPa. Surface elevation is 100 kPa, so it goes through that pressure cycle every time you take off and land. And as a result, you get fatigue cracking as a result of the number of cycles of pressurization. And so you could proof test that by doing that on an airfield and see when it finally ruptures the skin. And so that also is applying a pressure to the inside of the airplane skin to see exactly why it behaved in this mysterious way that you didn't want to. What else have we got? Oh yeah, I think this is an animation as well. Perhaps not in your time. I can't see the. You guys are 20, so that's 2005. So I think before your time. But this is Aloha Airlines flying between the Hawaiian Islands. Lots of takeoffs and landings because they are short transit times, so you can squeeze many of them into a day. And again, the problem of fatiguing, and also added with perhaps a salty atmosphere. And so it ended well, I think, except for one flight attendant who could not be restrained by the people sitting in their seats. And so probably not the way you want to travel in terms of landing with such a beautiful view of all around you. And it did make it down, and everyone survived. So again, another reason perhaps why you might want to know something about magnitudes of pressures that are acting on things. And I won't talk about that. If you want to see the Dam Busters raids, then go and look at a previous edition of this class, 3.1. It was the Allies wanting to knock out we know that the Ukraine-Russia conflict is going. Not so long ago, mysteriously, one of the dams on the Don River was breached and flooded a whole bunch of land in the intervening areas between Russia and Ukraine. But this was to stem the industrial production. Energy is the key to industrial production. This is hydroelectric dams which were attempted to be destroyed. And the problem is that dams are pretty sturdy. I'll run through it. And in being pretty sturdy, then what you have to do is, if you want to breach them, as this is the case here, you have to get the explosive at the base of the dam, where you have all the confinement of the water around you as a pressure to be able to apply a force that would rupture the dam. And so to do that, the so-called bouncing bomb, you run a bomb down, this is, I don't know if they've got some pictures. It's a very fluid mechanics problem. Yeah, there it is. So you design a bomb, you make the approach to the dam, you release the bomb, you give it some spin. It's just like skipping a rock, and you end up being able to get it with the right number of bounces to go down at the base of the dam that you have. And I think maybe it was successful 3 out of 4 of the locations that they tried. So to try and bring the war effort to the end in Europe in the 1944, I would imagine it is. So that's some of the motivation for the kinds of things that we'll talk about today. So we'd like to be able to not necessarily destroy things, but work for the public good. And so what we'll do is we'll talk about the issue of pressures on structures. So we'll spend the next 3 sessions talking about that. As is our plan, we'll do a very brief review of what's going on so far. So we know from pressures at a point, we have, a couple of equations of relevance. We know that everywhere that the change in pressure with elevation is equal to negative unit weight. The negative is because the positive values that we have are positive upwards. This is pressure, and this is negative Z, this is positive Z. And so from this we know for an incompressible fluid, P0 equals, no, P1 equals P0 plus or minus gamma H. And so this would be P0, this would be P1, this would be plus or minus H. And we make the distinction using H here instead of Z because Z is always positive upwards. And so we need to make a judgment call as to whether we're going down, in which we're adding pressures, or up, in which we're reducing pressures as we go through our manometer equation. So going down, we'd be increasing pressure, right? In going from here to here, we'd have to increase pressure. In going from here to here, we'd have to reduce pressure. So that's the reason for that. We know that at a point, if we choose pressure distributions in a fluid, and we think about this as being the water surface, then we know that just like this diagram here, if we go horizontally, then we find ourselves at the same pressure at these 2 points, even if there's a wall between us, and we can go around that wall, right? We know that. We know that we're lucky that in a compressible fluid, we know that the unit weight of gas is approximately 1,000th of the unit weight of a liquid. And so we can take that as 0 if we go up and down in the manometers. And if we know that if in the barometer example, put it upside down, if we get a gap at the top of the tube, if it's evacuated, the question we had just now, then this is equal to the vapor pressure, which is almost 0 for hydrogen, mercury, Hg, which is why it's used. The reason mercury is used in the barometer is because it's very dense, 13 times denser than water. So the height you need to be able to measure atmospheric pressure is 13 times less. And also the vapor pressure is tiny compared to water. It's very small compared to water. Water is very small, but mercury is much larger. So those are the things that we talked about. And we did some examples with manometers, and we also did some examples talking about pressures on surfaces, if you remember. And if you remember, we talked about this concrete step. The other question that we had this morning is that the other way that we thought we could solve it, instead of just balancing weights of concrete and pressures acting on the base, we could just do a free body that included just the steps themselves, in which case the pressure acting on this upper step was given by its location relative to the top of the concrete. This is the free surface of the concrete. The depth would be h down here multiplied by the unit weight of concrete. That pressure would act at a point. And I guess the other thing that we know is that pressures act the same in all directions. So Px equals Py equals Pz. It wasn't on that manometer equation. And so the maximum pressure acting on this step is going to be the vector which has the maximum component, which will be the one normal to it. So the pressure acting at this point will be in all directions, but we only care about the one which is normal to the surface because that gives us the force that applies here. And you've actually used that already, right? You might remember that in your first homework, you were asked about a 3-inch diameter bubble, not a round bubble, and you'd have to calculate the forces acting down here. You would calculate the forces acting up here inside the bubble, and you'd have taken that as a pressure inside the bubble multiplied by an area, and this is a pressure, and so the force acting upwards would be equal to pressure times area. That's all we're doing here. The force acting upwards is the pressure that's acting at this point, which we know how to calculate from last week, but now we'd like to be able to calculate what the magnitude of the force is that's acting. So we can calculate the forces that are acting on the abutment of the Malpasset Dam, or that are acting on the skin of the Comet airliner, which would be acting against the strength of the airliner, tensile strength. Or I guess we could also think about a balloon. We talked about balloons as well. That's a much better balloon. And so we know that if we want a balloon to go up, we haven't done it yet, but we know that the density of fluid in the balloon relative to the density in the atmosphere has to be, right? It's because of forces inside it. We'll find that out in due course. And so if we want that to be the case, the conditions for a balloon to rise, you can calculate from the ideal gas law. Absolute pressure is equal to density, gas coefficient times absolute temperature. If you rearrange that to get the density, you can get that as a function of pressure over ideal gas constant and temperature. And so if you want to be able to satisfy this relative to the atmosphere, then you can reduce the pressure, or you can increase the temperature, or increase the gas coefficient. Two of those are tenable, right? Hot air balloon, you increase the temperature. What's the guy's name? Louis de something, the guy who first did it in Paris and whenever, in the time of King Louis the something. I guess there are lots of them, up to 16. You can change the gas constant by substituting air for helium, as the Stanford kids did in our view of the Bay Area. P is much more difficult to do. So you can't really reduce the pressure because you know that in a collapsible balloon it'll just collapse. If you had a skin that was rigid and you could reduce the pressure, then that would be viable. But the problem is that a skin that is rigid is going to be heavy and is going to contribute to the weight that's acting down in addition to just the gases that is. So this is the weight of the balloon, if you like, counts. And so this isn't very easy to do because it will just fold on you. And actually things are much less sturdy in compression. If you take a Coke can, empty it, and then you put a bicycle pump on it to inflate it, you know that you can ping it and it will carry pressure. But if you reverse the pump by changing the plunger's direction and suck air out of it, you know that it will collapse, it will crimp, because it will change in a different mode. So neither here nor there for this class, but anyway. So that's where we are with the stuff that we've talked about so far. So what we're going to do is talk about pressures on structures. Why do we care? We know. I don't know what this is, so I won't even talk about that. Oh yeah, one of the things was a turbine generating energy from incoming waves, which we didn't go through. And so there are a couple of things we want to be able to calculate. And what we'll use some standard results. And so today I want to develop these standard results, but we'll ultimately come back to defining them and using them as is. So if you get bored with the derivations, then you can take solace from the fact that you need the final results not to be able to derive them, but it's useful to be able to say where they come from. The reactive force that's acting on a system is equal to the unit weight times the depth of the centroid times A. We'll talk about how we get this. The resultant we can get because if we were interested, perhaps I'll do them in order. This is an easy one to talk about. What happens if we have a force acting against the dam, which represents, don't do this red one, this represents the pressure that's acting here. Oh yeah, actually let's leave it there, acting here. In addition to the dam, we have the weight of the dam acting downwards. And if we know the weight of the dam and the force acting to the side, we should be able to do something to be able to look to see where the resultant of these two forces lies relative to the tow. If we know where this water pressure acts as an average force and where the weight of the dam acts as an average force, in other words, the resultant, then what we would find is that we could do something like this. And this would be, I don't know, I won't call it M, I call it F actual. So this is a result of water, this is the weight of the dam. The resultant of those two forces is their vector sum, which is this. And the resultant that is acting as a result of these two, this would be, in this particular case, FA. And the utility of doing that is that FA, for instance, if we know where these act from, if FA was outside the tow, then it would mean it would fall over like a domino. And we could calculate that. So that's one reason that we're interested in that. So let's not worry about that now. So we're interested to know what the resultant force is. We're interested in being able to resolve forces. And we also want to know where it acts. And so, yeah, all right. Actually, let's do it a little bit differently than I usually do it. So let's say if we fill up a dam to this point here, so that we have the forces are acting on this inclined surface. And we dry out the other side. So what we could do is we could define a horizontal plate. And so this is the plate of the dam. This is the dam, vertical dam side. This is the horizontal dam side. We're putting water here. This plate is where the pressure is acting. From what I've just said, it acts in all directions on that dam, but we're interested in the one vector that acts normal to it, because that'll give us the maximum force on here. And so my attempt to do this is to take this coordinate system. This is going to be X, this is going to be Y. I'm going to draw some parallel lines. And I'm going to do this. And need a wider brush so I don't have to do it so many times. So this is our plate. We can define a couple of locations. Oh, not that. Go back to this again. So I can run a line from here to here, bless you. And I'm going to define some lengths. This length will be what I'll call YC. Below YC, I'll do a length which I call Y uppercase R. And I'm going to do this as delta YC, delta YC. Yeah, okay. And in other words, in this geometry, I'm not sure how I can draw it. Perhaps I can draw it here. If I was to draw this, off to the side, this would be the pressure prism that is acting from the surface. So this is where it intersects the water. So I guess the water, if I do it in blue, would be a horizontal line here, right? So this is, purple is here, water surface is here, this pressure prism, triangle I guess, not prism, is coming out here and acting on it. If I were to take this and fold it from corner to corner, like this, and if I would take it and do the other one, do it corner to corner, like this, if I can do it. This gives me a point where these two lines meet, which is the green dot. This is the centroid. So if I wanted to balance my basketball, that would be the point where every single lever arm with a weight of paper acting on it from this point is symmetrically disposed so it balances here. So there's a lever arm. I don't have a pen. I could write a little dx dy volume here with a lever arm from this point, and if you went all around this thing, this point, they'd all balance. If I had a knife edge for this and I put it on that knife edge, it would balance here, it would balance here, and it would balance at every intermediate point that I put it through. The centroid. So you know the centroid from your math. So the centroid is evaluated, and always, this is true, the resultant force that acts is equal to the unit weight of the fluid multiplied by the depth of the centroid below the surface. And so the depth of the centroid will be this vertical height here, which is this, and it will be the area of the plate, which, if I am artistically inclined, will be this area, right? That's code. So it's going to be, I guess I think in our calculations we'll call this B, and we'll call this A. Let's see if, let me check that. I'll come back to it in a second. I'm just going to check. Looking for standard results. Too far down. There. Yes. B, A. We'll come back to this. I just want to use it'll easy if I use the same terminology, not technology. Okay? Are we there? So if you know what B and A are, BA. If you know what the depth of the centroid is below the surface, this vertical distance here, and if you know where the centroid is, of course, it's the balance point, it's the center of gravity of this, right? This has gravitational attraction for all the weights of the pieces of paper. It could be a piece of plyboard or something, in which case the weight of the board would be more obvious. And it's just the balance point where all the lever arms multiplied by the small weights balance out across it. And you need the unit weight of the fluid. The reason this works, if you wanted to do it, I don't know whether we want to do the derivations. If you take a vertical plate and you look at the, so this is this. So this is X, this is Y. What would we do? You want calculus, right? You really want calculus. You're missing out. dy. This is B. If I just draw what would happen to the pressure prism as you go down, it's like this, right, on the vertical plate. So this is what? P is equal to unit weight of the fluid times depth, y. I'm doing y positively downwards. We would have a force acting against this, which would be, why don't the colors come out? Force acting here would be pressure times width times dy, right? Pressure times an area is a force. So this is equal to what we'll call uppercase P. And so we can write the fact that force is equal to pressure times B times dy. This is the change in force. So why don't I get rid of this and call this dF. And so I think we've got everything we need. We know that this is this. So we could write dF is equal to unit weight times B times Y times dy. We could integrate both sides from 0 to y equals h. And we'd get F is equal to unit weight times B half y squared. And if we split that up, we'd end up with FR is equal to unit weight times a half. Okay, so I have to substitute limits for this, I guess I forgot. 0 and h. So this will become half y, h squared. So this will become, didn't do that, yeah, h. And get rid of this. So this is equal to unit weight h times b. I think it's right. My math is usually horrible, but I'm pretty sure that's right. And I'm pretty sure that's right because it echoes exactly what we have here. We have a resultant force. It's equal to the unit weight. It's equal to the height of the centroid, vertical sheet, h, half h, which is this point here. and it's equal to A, which is the height times B. So this is it. So could have done it by calculus, but so this is a standard result. The other thing that, if you don't care about the calculus, the other reason why this works out is if you think about it, and if you think about the pressure prism, P versus elevation, or depth rather, Y, that the pressure prism looks like this. So all of these individual arrows, I won't draw them all just because it's too tedious, look like this. We know that the magnitude of the average force looks like it is because what we could do is we could take half of this. This pressure would be what? If this is H, the pressure at the base, bless you, P is equal to H gamma. So if we take half of this pressure, then what we could do is we can take this area here and move it to fill up this gap here. And so, by definition, the pressure that's acting is going to be equal to half the pressure, right? Because we're moving this triangle here to fix for this one. That means that this is just a prismatic distribution. This prismatic distribution is equal to the pressure at a half H, half height. So actually the other way to think about this is that if the resultant force is equal to the unit weight times hc times the area, then this is just the average pressure that's acting. The average pressure is acting at the centroid because we can take this little triangle and move it here, by definition, to make this a vertical line. So that's defining it at a whole bunch of different angles. But in the same way that we define that this is always true, absolutely. This is only true if it's an incompressible fluid, but this is always true. Then this relationship that we have, that the resultant force is equal to the unit weight times the depth of the centroid, which is the average pressure acting on the plate, and multiplied by the area of the plate. The plate can be a rectangle, it can be a triangle, it can be a circle. You just have the appropriate location of the centroid. And the other thing that it can be is it could be that the water level would be, say, this is the surface of the water, and maybe the plate is here, in which case the pressure acting on that plate would look something, would look something like this. Again, this is the pressure with depth. I don't know if I did it so it would work out. I don't want to do that. Maybe imagine if this plate was continued all the way up to the surface. Did I do it right? I might have done it right, actually. It wasn't very cleverly drawn. This obviously has to go to 0 at the surface. It kind of does. But maybe I don't want to complicate it by doing that. But now, this would be the depth of the centroid, vertical depth of the centroid, h sub c. This magnitude is the average pressure. So this is unit weight times h sub c. And if you draw a line through that like this, then you have adding a bit here, subtracting a bit here, exactly the same as this. So, bottom line, always true. The resultant force that's acting normal to this is going to be Fr. You'll notice that I didn't draw it through the centroid because it does not act through the centroid. Almost never does. Actually does if it's horizontal for our stair step, but it will always be below the centroid. And likewise, in this case, FR would be here. Always acts perpendicular to the plate, right? So I'm trying to be as plain as I can. The more difficult one, I don't necessarily want to do the derivation. And my reason for drawing this figure is that the resultant acts through the center of pressure. And the center of pressure is given by YR. And so when I drew this sloping figure, it doesn't have to intersect the water, but it did in the picture we drew. Then I specifically drew the depth to the centroid as h sub c, but I specifically drew the lengths in the plane of that flat plate in the plane of the flat plate, y sub c. And we call them different things. We call them h versus c. And so the slope distance to the centroid, this is the centroid of this plate, is this. But the location where the force would act, I'm not sure if I can do a very good perspective drawing, FR in this particular case would be acting normal to this plate. It would not be acting at the centroid, but it would be acting somewhere below it, always below it. Can be equal to it if it's horizontal, in it if it's horizontal, but otherwise would be below it. We could derive it. I don't feel like deriving it today. You probably don't feel like a receptor for a derivation today. Do you feel like a derivation today? I'm a funny guy. Come on, cut me a break. Well, we won't do it then, but we will look at how this works. Okay, let's see if I can do that. Let's see how clever I can be. Oh, very clever. I feel clever today. Can I do this? Oh, no, I thought that was the case. So, let me take it. IXC, I can make it so. So, FR acts at the center of pressure, the COP, at Anfield. And the location of the center of pressure is YR is equal to the second moment of inertia about X XC. Second moment of inertia of the centroid about X divided by the in-slope distance to the centroid multiplied by the area of the plate and added to YC. Okay. So these are all the dimensions. YC is the distance from the surface. Actually, in this case, it's to the plate. But if the top of the plate didn't intersect the surface, it would be the distance to the surface. We'll deal with that in a moment. And this is the so-called second moment of inertia about the x-axis for the centroid. Sounds complicated, but you've seen it if you've seen structures and beams in statics. It's a standard result for a plate that looks like this. That we've dealt with. This along the top is B, this is A, I, X, C is equal to B times A cubed over 12. I think, I'm going to check in a second, just to make sure. It's the stuff we looked at before. This is all in Munson, if you have Munson. This is B A cubed over 12. This is the centroid of the plate. So this would be YC. essentially. And this would be width B, depth, which could be vertical depth or it could be angled depth, A, side of the plate. So on our plate that we use, this would be B, and this would be, well, we unfortunately called it H, right, because we're looking at a vertical plate, but that's kind of ambiguous. So if we do that, I didn't mean to do that. Guess I got super big. And we'll talk about this when we start off tomorrow's Wednesday's class. Sorry about all the scrolling. So if we wanted to calculate the depth at which it works, we could do this. YR equals XC. So it's going to be BA cubed over 12. It's going to be YC, which in our particular case was equal to... It's okay, so I'm going to do it for the case that we've already looked at. So this is the top of the water level here. This is what we've also called H. So this would be HC. This would also be equal to YC. So this is a vertical plate. And so YC would be equal to A over 2. Okay, so write it as A over 2 here. Area would be equal to A times B. And this would be equal to A over 2. All I'm doing is writing this out in the terms that we have for this. So YR would be equal to, if I cancel these out, this would be lose this. We would end up with 2 over 12. We would lose this, and this would be 2. And this would be 1. So I guess I can get rid of that too, hopefully. And then this would be plus A over 2. If we rearrange that, that would be 1 over 6 plus 3 over 6 equals 4 over 6 equals, I've lost the A, which is 2 over 3. This needs an A attached to it, this needs an A attached to it, this needs an A attached to it. Okay. Bottom line is that YR is equal to 2A over 3, which equals 2 over 3H. Standard result for this case. So you have water going through a plate. How are we doing for time? Got 5 minutes. You have the pressure acting down as it intersects the surface. People zipping up bags, ready to bolt for freedom. And so what we find for this is that if we look at the things that we've talked about, FR, the resultant force, acts at, we've called this H before, so let's still call it, It acts at a depth of 2 over 3h. And its magnitude is equal to the unit weight of water, the depth of the centroid, and the area. And the centroid is a depth of h over 2. So that's it. So now you know how to calculate the magnitude of the resultant acted at any position, and you now know how to calculate the location where it acts. It is always given by this expression. And you'll note that the way it's divided up is it acts at the location of the centroid plus a small amount delta y. This is delta yc. And if you go back to our figure that we talked about, that's exactly what I have here. So you just need to orient everything. This is the key figure. We didn't do as many derivations as I usually torture people with, but you've got the result. So you have a width, you have a length of the piece of paper. It can be in contact with the surface or it can be way below it. It doesn't matter. You have to remember that if you want to calculate the magnitude of the force that's acting, you're using the depth of the centroid, which means the depth from the surface of the free surface of the fluid vertically to this point here, whatever that is. And if you want to calculate the location by which that acts, y sub r, then you need to look at everything in the plane of this inclined figure. Up to the surface, the origin is where the x-axis skips across the top of the water. The y-axis comes down along the side of this. So the depth in plane to the centroid is the depth from the x-axis to this point here. And then delta yc is a small amount below it, and that's physically where that acts. So now we know magnitude and point of action. And so we've done two of the things that we want to calculate. How big the forces are, and where do they act, we now know. And so now the other thing that will turn up in lots of the questions you do is kind of a failure mode. How do you look at how the dam rolls over to be able to resolve whether this force that's acting is a problem or not in your ability to design things? So that's where we're going. That's it, I think. Questions? Yep.